Good evening, all. Welcome to week 12 of live session for fundamentals of convective heat transfer course. Hmm, Give me a second. Few more students will join. So this week we'll be discussing on condensation and boiling, basically phase transfer. We'll discuss the difference between evaporation and boiling, and then we'll have something called pool boiling curve, followed by the upstream condensation on vertical plate and horizontal tubes. And subsequently, we will solve some problems based on whatever is covered in the lecture videos. Again, as I will be saying in last few lectures, this is expected to be kind of a summary one. So I would advise you to go through the lecture videos complete to get a complete understanding. If you have any queries, please to raise them. And tomorrow we'll be having 1 hour extra session from 5 to 6 p.m. wherein we can take up any questions you have. And that will be the last session for this course for this particular semester. So the common phenomenon, the difference that we observe between evaporation and boiling, are evaporation is a surface phenomenon, whereas boiling is a bulk phenomenon. And the major difference between evaporation and boiling is in evaporation, the vapor pressure is actually less than the saturation pressure at that particular temperature. However, in boiling, it would be a reverse way. So, for example, if you have a water surface that is like water evaporating from the surface of the floor, what you usually expect is the temperature of the surroundings versus the temperature of the water. If you see, the temperature of the surroundings will be higher. So the heat is being taken from the surroundings and water is getting evaporated back into the surroundings and not from the solid surface. Of course, in reality, you will have, for example, if you have a vessel or a container with water and you keep it on stove, then you'll have both evaporation as well as boiling happening simultaneously. So as we were, the entire course is based on determining the heat transfer coefficient and Nusselt number. So for this particular problem, Nusselt number will be a function of the Grashof number defined in this particular fashion. The difference that you have to see is the appearance of this term. Like previously, we are used to having here beta delta t. So instead of beta delta t, we are having delta rho now. And then we have a new number called Jacob number, which tells us which in a way tells us what is the ratio. This is specific heat versus the latent heat. So the ratio of specific to latent heats of transfer. So the specific heat transfer is because of this temperature difference, and of course latent heat will happen at constant temperature. So this ratio is given by the Jacob number. Prandtl number is already known, and bond number BO is a bond number which signifies the relative strength of the buoyancy force to the surface tension forces. And even in boiling, we have further regimes as pool boiling versus flow boiling, depending on what is the actual natural cause within the boiling phenomenon. So if it is a natural convection process, which is largely due to the buoyancy forces, then it is a pool boiling. If it is because of external pressure gradients that have been imposed by the particular application, then it is a flow boiling design. And then we also have subcool versus saturated boiling. So what that means is if the entire fluid is the entire boiling is happening and the liquid temperature is TL, then if at that if the liquid temperature is lower than the saturation temperature, then you call it subcool boiling, or in other words, so you know the boiling is happening, but the temperature of the overall liquid is less than saturated temperature, then it is subcool boiling. If it is greater than that, you will call it saturated boiling. And all of this lecture is focusing only on pool boiling. We have not gone into the flow boiling designs. So within pool boiling, so this particular case is when the temperature is gradually varied. So you have a heater, you put the heater inside, say, pool of water, and then you allowed it to heat. Like you maintain the temperature of the heater, you gradually increase the temperature of heater. So this temperature difference, T wall minus basically the heater temperature minus the saturation temperature of that particular fluid at that particular pressure. So for example, if this is water, at 1 atmospheric pressure, if the temperature is 100 degree, boiling point is 100 degrees Celsius, that will be the saturation temperature here. And we gradually increase the surface temperature of the heater. As the temperature is increased, what we usually expect is the heat transfer to continuously increase. But however, what is observed experimentally is initially when the temperature is higher, so natural convection will start. the convection currents will set in, and that will the heat transfer coefficient will be proportional to this delta T. But beyond a particular point, the bubbles will start forming, and then you will have something called nucleate boiling. If as the temperature difference keeps on increasing, then the rate at which bubbles are coming will also increase. So these bubbles will eventually combine with each other and form columns. So again, this will reach the maximum, like once the column reaches from the bottom to the top, then you will have the maximum heat flux that is happening. So that is called the burnout point. And if you keep heating beyond that particular point, then there is some transition zone, followed by which we will enter into something called a film boiling, where the surface of contact between where the heat source and the fluid will actually be now replaced with a film, vapor film. And because vapor film has lower thermal conductivity, there will be initially this, like, the minimum will be formed, and subsequently, because of a combination of radiation and conduction will happen across this vapor film, and then it keeps increasing. The heat flux keep increasing with temperature. So we identified like three or four regions here. So for each, depending on which regime you are in, the way you calculate heat transfer is completely different, because the mechanism for heat transfer is different in each of these regimes. So if you are in the first regime, so whatever we have been discussing in the last week, those will be the equations that you will be using here. However, in the last week we were discussing on vertical plates and stuff, but here it will be an horizontal one, so the Rayleigh-Bennet type of convection. And in the nucleate boiling, we'll have a different correlations that we have to use, followed by transition and film boiling. Each one has different correlations. You have to use the appropriate correlation for that particular scenario. In the next, so that is with respect to the boiling. The next one is for the condensation. So the simplest case is the condensation over a vertical plate. So the parameters that we are interested in is what is this film thickness, what is the rate at which condensation is happening, what is the net heat transfer from the surface. And these are the correlations that are given, and these are based on the assumption that the flow is laminar and we do not have any adverse pressure gradients. So it's just like whatever is the vapor here, the surface is at a lower temperature, the vapor comes in contact with that and it forms a liquid film. And there is no droplets. The film is like continuous film. That these are some assumptions. With these assumptions, these are the equations that are derived. Like you just take the Navier-Stokes equation and then you remove the terms one by one by apply the simplifications. Like you are assuming for this particular derivation, we are assuming that the velocities are very small and the effects of inertia are very small compared to the buoyancy forces. With that assumption, we ended up with this equation. And similarly, instead of vertical plate, you also have a horizontal tube like the one shown here. So here again we have the two things that are important are what is the average heat transfer coefficient and what is the rate at which condensation is happening. So these are the only things of my interest, and they are the quantities that are shown here. Yeah, so it seems more of empirical, like we do not have any derivation, like we do have derivations for these formulas. You can go through the lecture videos. For laminar case, however, if it is turbulent, then again we have to go with empirical correlations. But for laminar case, it's straightforward. You start with the Navier-Stokes equation. We have to use assumptions that there is no pressure gradient, and then we neglect the inertial terms. Then we'll be having a balance between the buoyancy forces and the viscous forces. So the only thing, like the buoyancy force is the one, the gravity is trying to pull the liquid downwards, whereas the viscosity is trying to hold it, make the velocity uniform. So the balance of these two forces will determine what the velocity profiles or what the mass flow rates and heat transfer coefficients are going to be. And again, this particular correlation is for the specific case that we are assuming that the wall of the horizontal tube is also at the more or less the same temperature as that of the saturated vapor. So under that assumption, the Jacob number will actually be 0, and we can write HFG directly here. Okay, we'll solve some problems to make it clear as to how to consider all these values together. So let's say I'll wait for some time so you can go through the problem. Consider you have a spherical vapor bubble of radius r as shown in the figure. The pressure and temperature inside the bubble are given as PV and TB. And of course, the vapor bubble has whatever the vapor pressure inside the bubble is higher than the pressure surrounding, otherwise the bubble will just collapse. The liquid is assumed to be saturated. So apply a force balance, like do a free body diagram and then determine what is the relation between PV, PL, and in terms of surface tension. So ideally you have to find out what is the radius of the bubble for these particular property values. For this particular vapor pressure and liquid pressure, what is the value of the bubble radius? That is the first part. Second part, if you use the classical Clipperian relation, which is given here given in the problem, whatever radius you are getting previously in terms of pressure and say surface tension, equate it in terms of the thermodynamic properties of temperature, thermodynamic temperature. And the last part asks you to actually calculate the radius of the steam bubble with for a given values of temperatures, surface tension, etc. This is a straightforward problem, so I'd expect you to solve this. Were you able to solve it? The first part should be straightforward. I guess you would have solved by now. So you have to do a free body diagram. Let's say if this is the hemisphere that you are speaking about. So if I cut this entire sphere into two halves, so I'll be having the surface tension force on this. And this surface tension force is actually the extra force that is actually keeping the drop intact. So the net pressure on this because of the vapor minus whatever is the liquid, the outside liquid ones, should be balanced by the surface tension force, right? This is the basic balance. So you have the liquid pressure acting and the vapor pressure that is acting from the inside. Both should be balanced, and that difference should be balanced by the surface tension force. And that is exactly why we need PV to be greater than PL, otherwise the bubble will just collapse. So now with this equation, we can directly get the value of R. This is a straightforward one. Of course, now let's say if I want to use the Clausius-Caprian relation, which is I know dp dt where this is a specific volume difference. Of course, we are talking about water, so VFG can be written as Vg. So dp dt is like I can approximate with this. But the question now is how do I relate, like how do I find radius in terms of this? But in order to find this radius, I need to know PV and PL. So it is given that the liquid temperature can be assumed to be saturated temperature. So let's say if I do the Taylor series expansion for pressure, the saturated pressure at TV, which is the saturated temperature TL plus some delta T. Hi. Yeah, so this is the problem I'm just presenting now. You can have a look at the problem. So as I was saying, so the idea is to get the radius of bubble in terms of temperature. So we can compute, like use Taylor expansion to get the pressure as like around the saturated temperature. So it will be P, and we are assuming that the liquid is at the saturated temperature. So this will be PL plus dPdt from, you can use the Clausius-Keplernian relation and you can replace that with this. At saturated temperature, this will be equal to TL times TB minus TL. So from this we can compute PV minus TL, and if you substitute that back in the radius, you'll be getting the equation for R in terms of temperatures. And the last part asks you to actually calculate the value of this radius, which is again a straightforward one. So I've just written it again in Mathematica. So you have to write like you're keeping that the net force acting on the bubble should be 0, which is PV times pi r square minus PL times pi r square minus sigma times 2 pi r should be equal to 0. And we are solving this equation for the variable r. And this is a solution like the one that I just shown now. The next one is you have to take the same equation but then use the Taylor substitution where PV is replaced with PL plus this is the dPdt term times TV minus T saturated. Once I do that, this is the equation for radius I'm getting in terms of the temperatures. And in this problem, the values of surface tension, HFG, all these values are given. So if I just substitute them, I'll be getting the radius directly. Okay, I don't think there are any questions in this problem. We'll move on to the next problem. So we have a pressurized cylinder vessel. The image is a little slower, smaller. Okay, you can see the image now. So the diameter is 20 centimeter and you have certain amount of water of height 5 centimeter in each. Of course, the top of this vessel is sealed with a relief valve so that if pressure rises above a particular point, the relief valve opens and the steam leaves. And once the pressure falls to that particular weight, so for example, the relief valve has a certain weight, just like a cooker whistle. So if the pressure inside from whatever the steam that is raising up is higher than the weight of that particular steam, the force exerted on that particular steam is higher, then it will actually blow off and then eventually come down when the pressure is lower. So that the pressure is maintained at a constant level and that pressure is given as 4.76 bar. So at this pressure, if the bottom surface is made out of copper and its temperature is maintained at 160 degrees Celsius. So assume nucleate boiling and calculate the total heat transfer rate from the bottom surface to the boiling water. And of course, you also have to verify whether that your particular assumption of this nucleate boiling is correct or not. How would you go about doing this? So how do you know whether this is nucleate boiling or not? The main criteria that we have is the excess temperature. So what is the saturated temperature here? Can I use 100 degrees Celsius? The key difference between this problem and the previous problem lies in this pressure. So if you see, the pressure is 4.76 bar. So at 4.76 bar, you have to use the steam tables and determine what is the saturation temperature. That would be the first step. Once you have the saturation temperature, we have different criteria depending on the excess temperature. If it is above 5 Kelvin and less than say 20 to 30 Kelvin, then you can assume it to be nucleate boiling. Of course, you can also have to calculate the net heat transfer rate, heat flux, and see whether that heat flux is lying within the maximum, like whether it is lower than the maximum heat flux, critical heat flux, which is the burnout point, which is this. So you compute the heat flux and see if it is less than Q max, and you can also see where the excess temperature lies. So it will be somewhere between yeah, so it will be somewhere between 5 and 20. So if it is in 5 and 30 or 20, so if it is within that range, you can assume the nucleate boiling. So that could be one criteria. And also you have to check whether your Q, whatever heat flux that you are getting using the corresponding heat transfer correlation, should be less than this burnout point. Then you can assume, then your assumption of nucleate boiling is correct. Okay. So this is the equation you have to use to calculate the heat transfer, heat flux from the wall, and all the properties should be taken at 4.76 bar saturation pressure, and I have given the property values. So all you have to do is take these values, substitute them back into the Brownian equation, into this heat flux equation. That will give you heat flux. But the question asks you to find the total heat transfer rate. So use that to find the total heat transfer rate. Like basically you have to multiply with that with the corresponding area. That will give you the total heat transfer rate from the wall. Once I have the total heat transfer rate, the last question asks you to verify the nucleate boiling assumption. So calculate the critical heat flux and see whether the heat flux you are getting here is lower than the critical heat flux limit. Then it is a fair way to check whether you are within the nucleate boiling design. Yeah, is that clear? Maybe I'll wait for a couple of more minutes so you can solve the problem yourself. Yeah, hope you have done it. You can just to cross check. So the pressure and temperature values are given. Again, I have used the same tool as before, wherein you can get all the property values directly and substitute them into the heat flux. So you can check whether you are getting the same answer. So this is around 4.2 kilowatt per square meter. That is the heat flux. Multiply with the area of the base. The base diameter, inner diameter is given as 20 centimeters. So just multiply pi d square by 4. That will give me the net heat rate to be around 132 watts. And the maximum heat flux is around way too high compared to this. For that, we use a different correlation, 0.149 times HFC rho V times this particular quantity, bond number, sorry, this quantity, which will give me the maximum heat flux. Again, this is an empirical correlation. So this is around 10 power 6, this is around 10 power 3. So you can see this is way higher than the QS that we have predicted from the correlation, which means we are still in the nucleate boiling design. Okay, is there anyone whose answers are not matching with the values that are given here? Or are there any questions? Okay. Are there any questions? Yeah, I guess there are no questions on this. Then we can move on to the next problem. This is again a very straightforward one. So we have a rectangular surface of a given length and temperature. It is suspended in saturated steam at 100 degrees Celsius. When the surface is oriented such that it is the length is aligned with the vertical, the steam condenses on the surface at a given rate of 0.063 kilogram per meter second. Calculate the condensation rate when the length L width makes an angle 45 degrees with the vertical. Also determine the film Reynolds number and the flow region. So what we are trying to ask is, say I have a plate like this that is vertical, and some condensation is happening on top of this plate. Now similarly, what, let's say the same plate is inclined at say 45 degrees. What would be the condensation rate? Which one do you think will be higher or lower? So if you just draw the two cross section, this versus this, the length of the plate is same in both the cases. The only thing that matters is the angle. So here it is say 90 degrees, and here we have 45 degrees. So this is case 1 and this is case 2. So which one will have a higher rate of condensation? Again, we are assuming it to be laminar and film condensation rate. Sorry, assuming it to be laminar and then film condensation is happening, no droplet condensation. So if it is assumed to be film condensation and still in the laminar regime, so which of these two cases will have higher condensation rate? Maybe I'll show you the question and wait for like 5 minutes or so. The idea is to understand how the mass flow rate is related with the angle of inclination. The heat transfer coefficient you already know how they are related with each other. It's already there in the lecture slides. You can go through the slides again once and get a quick idea of how it varies with respect to angle of inclination, heat transfer coefficient, and from that you should be able to uh, estimate what is how the rate of condensation is related with the angle of inclination. Or let me put that equation straight simply, then it should be fairly straightforward. Let's say if the heat transfer coefficient for inclined plate versus the straight plate, if I have to compare, then for the inclined plate, if I'm saying that is equals to whatever is for the straight plate times say sine theta to the power 1 by 4. If I say the heat transfer coefficient is related in this way, so how would the mass flow rate be related with each other? Like how would the mass flow rates relate with each other? Yeah, just give it a thought. I'll wait for say 5 minutes and then we'll discuss. Were you able to figure out the relation? So how do I get mass flow rate? The rate at which condensation happens is basically related with, so if I were able to calculate the net heat transfer, that would be the rate at which the condensation is happening times the latent heat, right? So m dot is related with Q is H times whatever is the excess temperature divided by H of G. So for both the plates, if this particular quantity is constant, then all we are saying now is m dot is proportional to H. What would that mean is m dot for the inclined surface will be m dot for vertical surface times sin theta to the power 1 by 4. So if you are not convinced with this equation and would like to start from the original equation, so you can start from there itself. So I will just show you a skip of that. So this is the equation for delta we have, and we know how is m related with delta. So all I'm doing is I'm replacing g with g sin theta, because in the governing equation we'll be having g sin theta term. So these will be my two equations. If I substitute delta into this m dot equation and then substitute theta equal to 90 will give me m in term at for vertical plate, and theta equal to 45 will give me for the case of 45-degree inclined plate. So this will give me the ratio of those two, and the ratio is 1.09. So this is straight to the inclined plane. So which means the for a vertical plate will have higher condensation rate, around 9% higher condensation rate than an inclined plate. That is essentially because the effect of gravity has reduced. And in this particular problem, we are also asked to find what is the film Reynolds number. So film Reynolds number is 4 times mass flow rate by mu L. All we need to do is get mu L, take the property at the film temperature, and substitute the mass flow rate that is given in the problem, which is 0.063 kg per meter second. So if I just substitute those values, and if that particular value is around 802 or something, this is less than the critical number for transition, so it will be in the laminar regimes. It will still be in the laminar regime. This is a straightforward problem. The only thing that you need to be like, either you have to remember these equations, or you have to come up, you have to remember the equation that I have written here, that the heat transfer coefficient is proportional to theta sin theta to the power 1 by 4. If you know either of these, and from that you will be able to estimate this relation, like get the solution. Are there any questions in this? I guess there are no questions. So similarly, instead of vertical and inclined planes, let's go in the next problem. Let's say vertical plate versus a horizontal cylinder. So I have uh, so say the saturated vapor is condensing on a vertical slab of height L. If both the sides of the slab are covered by laminar films of the condensate and a single horizontal cylinder of diameter d, same temperature as the slab is immersed in the same saturated vapor. So there will be some particular diameter d at which the condensation rates will be same on both the plate as well as the cylinder. What is the d by L ratio at which this happens? I hope the question is clear, or to just elaborate it. So basically I have a flat plate, vertical plate, and then I have a horizontal cylinder. So all I'm saying now is there will be some condensation rate associated with this vertical plate, and then there will be some condensation rate associated with this horizontal cylinder. So what we are saying now is I want m dot v equal to m dot h. With this equation, what will be the value of d by l? This is also just like the same previous problem. All you have to know is how are the heat transfer coefficients. Like if you know the equation for the heat transfer coefficient, from that you have to estimate the equation for the mass flow rate or the condensation rate, and take the ratio of these two quantities equate it to 1, and that should give you the value of d by l. I think this should take 5 minutes to solve. I'll wait for 5 minutes. So are you able to get the solution? As I said, the heat transfer coefficient, you can take the correlation from the lecture slides. So this is a correlation that is given. Of course, it depends on the Jacob number. For this particular problem, we are assuming that the wall is at the same temperature as the saturated paper. If that is the case, Jacob number will be equal to 0. And the next part is from the heat transfer coefficient, I need to get m dot. I have shown the equation just now. So m dot is basically q divided by hfg, and where q is h times delta t excess. So h into the area is L times T saturated minus T wall temperature divided by HFG. So if I substitute that back into the equation, I'll be getting the equation for M plus. Similarly, M cylinder, the mass flow rate for the cylinder is also given in the lecture videos. So you can go through the slides for that. The question now is we are trying to equate mass flow rate of the condensation rate for the plate as well as the cylinder and determine the value of d by L. So all I'm doing is substitute L equal to 1 and get the value of d. That should give me the solution. So I'm getting this around 0.77, which is close to around 5 by 4 or something. If you want to take 5 by 4, so that is around close to 0.785 or something. So for d by L equals to around 5 by 4, we'll be having the condensation rates to be equal to both of these values. The key thing to note here is, I think I missed that out over here, but there is one thing that to notice here is in case of the equation that I have written here, 1.923 times whatever I have written here, this equation is for which sides? Like, is it on the both sides of the horizontal cylinder, or is it for only like half of it? So if you were to see this equation, so the condensation rate equation that is there in the lecture videos, this refers to only on one side of the tube. You can refer to the previous one as well. Yeah. So this is only on one side of the tube. That's exactly the reason I have used, even for the plate, the flow rate I'm considering, I have just put L here. Even though in the problem that's specified as both sides of the slabs are covered by laminar films of the condensate, which means I should ideally be using 2 here, 2 times L, but I've just cancelled that 2 directly here. Like ideally this will be 2 times H plate times L times this, and this equation will also be 2 times this entire equation. Since we are equating M plate, both the flow rates to be equal, the 2 will get anyway cancelled. That's why I've not included them here. But if you're getting confused, then maybe I should just put that here. So it will be clear when you see the solution at a later point of time. This too is just to ensure that both the sides are being taken into account. Of course, the answer would not change. Is this clear? Yeah, I guess that is clear and there are no questions on this. Okay, then we move on to the next problem. So this is the last problem I have. So consider you have a horizontal thin wall tube shown in the figure, cooled by an internal fluid of temperature Tw. The tube is immersed in a stagnant atmosphere at saturated vapor, which condenses in laminar film fashion on the outer cylindrical surface. It is proposed to increase the total condensation rate by flattening the tube cross section to the shape shown on the right side of the figure. Calculate the percentage increase in the condensation flow rate associated with this design. So I have two possible designs available to me. Either I can have it as a round tube, or with the same perimeter, I can take the same material and then make it like a flat tube. Here, the condensation will be happening on the surface. Again, the fluid will fall like this, like a film condensation. Here also the film condensation will happen. Which one of them will have the higher condensation rate, and what will be the percentage increase in the condensation rate? So here it is proposed that By converting into a flat tube design, your condensation will actually be higher compared to this, because you know the effect of gravity. Here, gravity is actually acting in the same direction, so it will be the strongest force. However, here what happens is only a component of the gravity will be acting on the surface, so the effect of the pulling force from the gravity will actually be lower, so the condensation is expected to be lower here compared to this one. The question is how much percentage it is going to be higher when you use the flat tube design. I think the question is clear. So it would be very similar to the one that we solved just now. What we have to do is, there is only one trick in this. How do, like in the previous problem, we are trying to get the ratio of D by L. In this problem, the ratio of D by L is given to you indirectly, and you are expected to find what is the mass flow rate. So like in the previous problem, we were given that for the plate as well as the cylinder, the condensation rates were equal. What would be the value of D by L? In this problem, D by L is given indirectly, and you're asked to find the ratio of the condensation rates. So all the correlations, etc., will remain similar. So if you want to see the correlation, I'll just show the same equations. So these will still be my correlations. This will still be my the same correlations. The only difference now is I'm trying to use the relation between D by L, as the perimeter of both the cross sections are going to be similar, which would mean that L will be equal to pi d by 2. So pi d is the perimeter in case of the round cross section, and for the flat plate, we'll be having 2L as the perimeter. Like we are assuming the thickness to be very negligible. So L is approximately equal to pi d by 2. With this assumption, if I substitute it back into the ratio of plate to cylinder, I should be getting the, so I'm getting around 1.15. What this means is by converting from a round tube to a flat plate, I'm getting around 15% increase in the condensation rate. Maybe I'll wait for a couple of minutes so you can solve it yourself and let me know if you're getting the same answer. Yeah, I hope you got the same answer. Are there any questions? So these are the questions I have. To summarize what we have been discussing this week, we started out with the boiling curve, the difference between evaporation and boiling, followed by what is the pool boiling curve, and then we identified different designs within the pool boiling versus natural convection, followed by nucleate boiling, followed by transition and filling boiling. Out of these, each one has different correlations that have already been pointed out. The correlations have been pointed out in the lecture videos. Subsequently, we went out into condensation and we solved the case of laminar condensation over a vertical plate followed by a horizontal tube, and then when you have multiple tubes also, that has also been discussed in the lecture videos. And with these we have solved some problems where you can actually determine the heat transfer coefficients based on the thermodynamic properties of that particular fluid. As you see, like most of these course, all these problems would actually be amounting to identifying the Nusselt number correlation. Once you have the correlation, all you have to do is take the material properties, substitute them, get the heat transfer coefficient, get, and once you have the heat transfer coefficient, either you're asked to find the temperature or you're asked to find the heat transfer. These are the only things that you'll be asked, and all the questions are based on that. Yeah, so there are no questions, and I think we can end the session for this week. And tomorrow we'll be having an extra session. So I'm planning to have a summary of all these lectures with some important correlations and some concepts. Like I'll not go too much into concepts. Maybe I'll present you with some correlations and maybe one or two sample problems. It's supposed to be around an hour or so. If you do have any questions, then please do join the session and get your questions clear. Yeah. Are there any other questions? Or maybe if you want, I can just go through the part where we have multiple tubes also, because I've not taken up the problem on multiple tubes, so we can go through that part as well. So this is for one tube. We have solved problems up until here. But let's say when you have multiple tubes, like something like this, an array of tubes in different fashions. So here it is in a straight line. Of course, it need not be in straight line. It can be staggered as well. Depending on configuration, the as could be different. But let's assume that you are in this particular range where you have a thin sheet of film, so that you are still in the laminar design, film condensation is happening. It's not like the droplets that you're seeing here. If this is the case, all we are saying now is if you have n such tubes, between any of these tubes, whatever is the mass flow, like for the first tube, all the equations remain same as before. However, as this liquid will fall on the surface of the second tube, here we'll be having an extra mass flow rate, additional flow. Like if I consider a CV here, so I'll be having an extra inflow here, unlike the first tube, and that keeps adding up as I go down to the, like as I go downwards, the extra flow rate from the top tube should also get added to it. So we'll start with the same equation as before, just rearrange it a little bit. All we are doing now is this correlation, which will relate how the mass flow rate between these two is getting affected. And from that, all we have to do is solve them simultaneously, one by one. So at initially, for the first tube, we do not have any n minus 1. So this is not there. So this is the equation that we already got previously. For the second tube, it will be the first tube plus whatever is the extra one that we are going to have from here. And as you keep increasing, this particular term gets added eventually. You might actually have. Yeah, are there any questions? Yeah, you might have actually asked why didn't I do m dot plus, like for example, I could have done directly m dot, but why am I worried about this 4 by 3? Yeah. So basically I want to have, like when I do this equation, yeah, so you'd want the same temperature difference to be occurring everywhere the temperature T sat minus, the T saturated minus TW or whatever the supercooling, the subcooling that is going to happen has to remain the constant. So for that to happen, we have to rearrange this in this particular fashion. So your delta T will be proportional to this one. So for all of these tubes, the delta T will remain the same. Okay. And once I have m dot at any particular point, all I have to do is take the heat transfer coefficient which I have for that particular case, which we already have, the equation we already have before. So all that we are doing now is whatever is the this is the mass transfer, mass flow rate, because m dot Tn is only on half side of the tube. So on both sides it will be 2m dot times the latent heat should be equivalent to average heat transfer coefficient times the net surface area up until that particular tube times T saturated minus TW. From this, we'll be getting the average heat transfer coefficient. Once I have the heat transfer coefficient, I can compute the Nusselt number. Just make a note here that in order to get this Nusselt number, we are using the characteristic length as n times d. And just substitute those values back. Now this is another flow. Again, all of these are based on the same things I have said before. Most of these correlations will be there. All you have to do is pick the right correlation that is applicable to your particular problem. So in your particular problem, you have to know what is the corresponding number. So in this case, if you know the Reynolds number, get the Reynolds number, check for the corresponding correlation in the literature, use that correlation for say usually this will be presented in terms of Nusselt number. Get from that Nusselt number, determine the characteristic length and other properties, use the value, get the value of heat transfer coefficient, and from that either you find the temperature difference or the heat transfer, whichever is your object of interest. And this is also one problem we have solved, is identifying the regime in which your particular flow is. So if the film Reynolds number is less than 30, you can assume it to be laminar. The one that we solved before is around 800, which falls in this particular regime. So you can consider it still to be laminar region, but wavy. And if it is greater than 1800, you can consider that to be turbulent region. And the last one is on inclined planes, where you related, okay, here the angle is here. In the one that I mentioned, the angle was supposed to be here. So then it was sine theta, but because the angle is here, it is cos theta to the power 1 by 4. From this, what we came previously is m dot will also proportional, the rate of condensation is also proportional to the heat transfer coefficient. So m dot inclined will be m dot vertical. I'll just use the notation that is used here. So that will be cos theta to the power 1 by 4. Again, of course, this relation is valid for laminar film condensation only. And the other assumption that theta should be less than or equal to 60 degrees. This equation is not true for horizontal planes. So with this, I would like to conclude this today's session, and we'll meet same time tomorrow from 5 to 6. I would like to, as I said before, I would like to have the summary of all this week's lectures, focusing mainly on the important correlations, their reasons of applicability. And if you do have any queries, we can discuss them as well. Thank you for joining.